Okay, great. So it's a great pleasure to have Tom Iadecola with us today. So he did his school mostly on the East Coast. So he went to Brown first, and then he did his PhD at Boston with Claudio Shamon. And after that, he was a postdoc in Maryland, and now he's assistant professor at Iowa. And so he's interested in, topological systems and quantum dynamics. And today he's going to tell us about some dynamics in cellular automata. So Tom, please go ahead.
Yeah, thanks very much. Thanks for having me. It's always a pleasure. Today I'm gonna talk about how we can leverage some pretty interesting classical systems with discrete state spaces that are called cellular automata to engineer or realize classes of quantum models that essentially have quantum many-body scars. So this talk is going to be a little bit about automata, a little bit about scars, and just to set the stage a little bit. So what I'm going to be talking about here is the dynamics of isolated quantum systems. So what that means in practice is that we're interested in kind of experiments of this type, where we prepare first a simple initial state, for example, a product state, and then we imagine that we have the ability to evolve the system unitarily under some potentially time-dependent unitary evolution U of t. And then after some time, we measure some local operators, for example, the magnetization. And what we're interested in, because we do physics, is we're looking at the dynamics of this observable as a function of time. And we're primarily interested in, for example, what is the late time average of the observable? What are its fluctuations? And we have ways of thinking about this, but it is kind of a challenging, task in general. So one kind of nice way of thinking about this kind of dynamical experiment is to think about essentially the infinite temperature dynamics. So by that I mean, you can construct basically a set of say Fock states or other low entanglement states in your Hilbert space, which are represented by these orange dots. And then you can draw sort of a bond between any two Fock states or other low entanglement states that are connected by the dynamics under your unitary. And then the infinite temperature dynamics is basically just saying that, basically the system is going to explore everywhere that it can in this sort of connected space. So it's going to explore basically the system, if it starts out in one node, will have the ability to explore every node that it can reach via the dynamics. Okay, so we just kind of assume that the system can explore everywhere that it's connected. And we can kind of organize ourselves, we can organize how we think about different types of quantum dynamics along an axis that you could call Hilbert space connectivity. So how connected are the states in my Hilbert space under the type of evolution that I'm considering? And I've kind of highlighted two extremes here, which are ergodic and many-body localized. And lots of people here have worked on this and done pioneering work. But for example, an ergodic system, we have essentially all-to-all connectivity. If you think about systems that you could reach asymptotically, at least constrained by, for example, the symmetries of the system. Obviously, if your dynamics respect some symmetry, you won't be able to reach a state with a different symmetry eigenvalue from your initial state. And in general, these systems, if you have some conserved quantities, you get hydrodynamic transports of these conserved quantities. And the entanglement in the system kind of spreads in this sort of light cone fashion. So like if you're in 1D, you have this linear light cone for entanglement growth in your system. And then at the other extreme, you have many-body localization, which Zlatko and collaborators showed, essentially you can think of as resulting from the existence of emergent conserved quantities in your system, an extensive number of emergent conserved quantities. And in this scenario, every eigenstate in your system can be labeled by selecting different eigenvalues of these emergent conserved operators. And so, in this sense, you can think of it as, once you sort of diagonalize all of these local conserved quantities, all of your states are kind of disconnected from one another in some kind of asymptotic sense at strong disorder. And what this means is that you have absence of transport as opposed to hydrodynamic transport, and you also have slow growth of entanglement. So entanglement grows as the log of time t as opposed to t. And one interesting question that that people have been asking a lot recently is, what happens between these two extremes? Okay, what are the sort of paradigms of Hilbert space connectivity that interpolate between MBL and ergodic? And so, we can kind of highlight some of those. One is quantum many-body scars, which is something that I'll be talking about today. And these are systems where essentially the system looks, for all intents and purposes, like an ergodic system, except you have maybe some special subspace of low entanglement states which are disconnected from the rest. So if you're able to initialize the system in an initial state that sort of has all of its support on this sort of disconnected cluster of the Hilbert space, the dynamics is going to look very different, and it can maintain its coherence. And I'll talk a little bit more about this. And you can kind of dial up the extremity of this kind of partitioning of your Hilbert space. For example, you can end up in a situation where you have what's called Hilbert space fragmentation. And here, the system kind of breaks up even more. So this is all within a symmetry sector, right? So we have these disconnected clusters in Hilbert space, which are not labeled explicitly by global conserved quantities in your system. They're rather, little pockets of Hilbert space where you can have varying degrees of connectivity. So you can have isolated states that don't couple to any other states. You can also have states that just kind of couple to some, say, order, some constant number of neighbors, for example. And you can even have like clusters where there's higher connectivity or even all-to-all connectivity, but they all kind of coexist. And depending on the cluster that the cluster or clusters that your initial state kind of has support on, your dynamics is going to be governed by what happens in these clusters. Now I can dial down the connectivity even further and consider what I'll talk about in this talk a lot, which are cellular automata. So cellular automata you can think of as having a special kind of Hilbert space fragmentation, where for example you only have basically any sort of Fock state is connected only to sort of one Fock state in the future and one Fock state in the past. So there's kind of deterministic evolution, and the system organizes itself into orbits. I'll get into why this is the case. I just wanted to kind of set up this spectrum of possibilities for you. And I should say that there are probably more possibilities than what I'm showing. And it's not really clear where the boundaries between all of these things are in some cases. But this is kind of one way of thinking about it. And in this talk, I'm going to focus on the connection between cellular automata, which are essentially classical systems, as I'll discuss, or they're sort of classical systems, or they can also be viewed as very special quantum systems. And there's a connection between these and the case of quantum many-body scars in sort of fully quantum dynamics. So that's what this talk is about. So what I would like to first review a little bit is what are quantum many-body scars? And I know that we have a very informed audience on this topic, so I apologize if any of this is redundant. But it's still worth going over this famous example of the PXP model. So the PXP model has a Hamiltonian that looks like this. It's essentially the Hamiltonian of a paramagnet in the x basis. So this xi is just sigma x on site I. But it's projected, that's what this operator P does, it's projected into a Hilbert space where spin configurations with nearest neighbor spins that are both up in the z basis are disallowed. Okay, so that's what I'm saying here. I'm basically saying that I'm not going to allow any configurations where nearest neighbor spins are both up in the z basis. And I won't get into the details too much right now, although it will be more relevant later, so I'll come back to it. But this is actually naturally realized in Rydberg atom quantum simulators in a particular regime. There was an experiment in such systems that generated a lot of interest in the community. The experiment in Misha Lukin's group observed basically these near revivals after a quantum quench from the nail state. So basically they followed the protocol that I depicted on the first slide, more or less. They prepared a nail state with alternating up and down spins that I'll just represent as 1, 0, 1, 0. And that's also represented here in this density plot. And basically they turned on time evolution in this regime where you have this kinetic constraint, or this so-called Rydberg blockade constraint. And basically the system was able to revive or return almost to the initial state that it was prepared in, despite the fact that this system is nominally, it doesn't have any obvious reason why you should have such coherent dynamics from an initial state like this, which actually has a very high energy density compared to the ground state. And then of course, Zlatko and collaborators came with this very nice theory observation, which is that these revivals can be basically attributed to non-thermal, quote unquote, scarred eigenstates that are defined by a couple of properties. One is that they have anomalously high overlap with the nail state, as I'm showing in this plot on the left. So the nail state is my initial state. Then of course, these states have very high overlap with the nail state. So the dynamics, when you initialize the system in the nail state, is going to be controlled by these special eigenstates. And they also have this property that they have very low entanglements. That's what's shown on the right-hand side here, compared to typical states in the Hilbert space. And I should say that there have been many papers about scarring, and here I want to just kind of define what I'm going to mean when I talk about scarring. So scarring in this talk means non-integrable models that have finite energy density eigenstates with subvolume law entanglement, as is believed to be the case in this PXP model, as well as, at the same time as perfect periodic revivals from particular initial states. Okay, so when I'm saying scarring, I'm going to demand that these revivals actually be perfect and that these eigenstates be sub-volume law in the thermodynamic limit. Okay, so by that definition of scarring, the PXP model has sort of approximate scarring. And it's a big open question, whether this model is proximate to some other model that does have quote unquote perfect scarring in the manner that I defined it. So the revivals are imperfect, they decay with time. This has been studied a lot. However, it's worth pointing out that there are many examples of physical models like the PXP model that have exact scarring. And I'm only listing some of the papers here, but there are many, okay? But this approximate scarring example is still very nice. One reason that it's very nice is that we still don't quite understand exactly what's going on. But another reason that it's very nice is that it has this appealing semi-classical description. So basically the fact that we don't know how to exactly describe the scar dynamics has led to some very interesting approximations that have very interesting ideas behind them, okay? And one is this semi-classical description that stems from the time-dependent variational principle. So this TDVP is basically a method of generating a dynamical system in a continuous phase space. So you're used to seeing maybe these kinds of like phase portraits or Poincare diagrams, like I've shown on the left for classical systems. And this TDVP is basically a way of approximating the dynamics in some manifold of low entanglement states in terms of a continuous dynamical system. And one thing that's been observed is that the initial conditions in this sort of classical phase space that lie close to regular regions, like this sort of region here that has a periodic orbit, or this region over here that has a periodic orbit. These initial states that lie close to these regular regions have slow, nearly periodic quantum dynamics. So even though this is kind of an approximate picture, it's extremely interesting because it suggests a connection between classical and quantum non-ergodicity. So somehow, the ability to obtain non-ergodic quantum dynamics in the truly, quantum dynamics of the system is related to some properties of a classical dynamical system. And this I think is a very interesting idea. And the main point of this talk is that we can make this correspondence exact for certain families of quantum Fouquet dynamics that encompass classical cellular automata. So what I want to think about here, this sort of bean-shaped region over here with a the cellular automaton sitting inside of it, that's basically like some space of possible quantum evolutions that contains as a special point in some, as yet undefined parameter space that I'll talk about later, there's essentially a classical cellular automaton sitting inside that region. And I'm going to argue basically, so these classical cellular automata are classical dynamical systems that have a discrete state space. And this discrete example of this classical system that has a discrete phase space has, there's a notion where there are basically quantum systems nearby in parameter space that have exact scars. Okay, so that's what I'm going to talk about here. So at this point, this is basically, I'm done with the introduction. I'm going to talk a little bit about automata next, but are there any questions at this point? Okay, perfect. All right, so I've talked about dynamics, now I want to, and scars, now I want to talk about classical cellular automata. So what are these systems? They're very interesting, very rich classical dynamical systems that are described as essentially a lattice of cells that you can think of as classical bits that can take two states, 1 and 0. So you can think, like in this picture on the left, which is going to become animated soon, 1 means, for example, that the square is white and the pixel is white in that picture, and 0 means that the pixel is black. And this lattice of cells essentially evolves deterministically according to local rules. So basically, I am going to update at each time step the state of a given cell based on the state of its neighbors. Okay, and there's a very classic example of this, which is known as Conway's game of life. And this is an example of the rules. So there's a birth rule where a cell that's in state 0 becomes state 1 if some number of its neighbors are also in state 1. There's also survival, which means that state 1 can persist from one time step to the next. And then there's also death, which means that an up cell in a cell that's set in the 1 state can evolve into the 0 state. And these are all conditioned on the neighbors. And the thing that's really nice about the system is that even though it only takes a couple of lines to write down the rules, you get these very interesting patterns that emerge in the dynamical in the dynamics of various initial states under these rules. Okay, and it can be extremely rich. For example, life is actually computationally universal, so you can actually simulate a Turing machine inside the game of life. I don't know why you would want to do that, but you can. So these are very rich systems, and they actually encompass, because this is computationally universal. You can put a Turing machine in the cellular automaton. You can simulate chaos. There's a sense in which, even though the system is deterministic, you can have analogs of chaos that arise in these systems. Now I want to talk about how is this relevant to quantum systems, and to do that we need to think about reversible cellular automata. So the game of life is not a reversible automaton, but any reversible automaton can be translated to a quantum circuit. So by reversible, basically what I mean is that any rule that can be run in one direction also is a valid rule in the other direction in time. Basically, the rules are kind of symmetric in the forward and backward time directions. So why does a reversible cellular automaton make sense as a quantum circuit? Well, remember that quantum circuits are composed of unitaries, right? So if we think about our computational basis as these sort of bit strings, which I can encode in integers, right? A reversible cellular automaton has injective local rules, and that means when those rules are injective, I can define a unitary U that implements those rules, right? Because unitary dynamics is always has there's always a way of inverting. There's always a way of inverting the unitary dynamics. You just take the conjugate transpose. So that means that reversible cellular automata can be thought of as special examples of Floquet systems. Okay, so by a Floquet system, I simply mean a system that evolves according to a quantum circuit that is just the repeated application of a particular subcomponent that I'll call U, and that's called the Floquet operator sometimes, or the Floquet unitary. So basically, the dynamics of some initial state psi of 0 out to time t is obtained by taking the power of the Floquet unitary to the Floquet unitary to the power t, basically. So I just repeatedly apply this operator. So we can think of them as a special example of a Floquet system not a generic, these aren't generic Floquet systems, these automata, because they have a deterministic action on the computational basis. So if I initialize the system in a computational basis product state, this particular kind of Floquet system, if I'm just applying the classical automaton rules, is just going to map computational basis states to single additional computational basis states. So basically, I keep applying this U, and I'm mapping one integer to another integer to another integer. And then because I have a discrete state space in a finite volume, that means that eventually, if I keep applying this thing and keep applying it, I'm going to have to come back to the state that I started in. Okay, so that means that every computational basis state lives on an orbit of length L. So this is something that I talked about in my second slide when I was showing these classical orbits of configurations that are connected to one another. So this is exactly what I mean when I say that. So these automata are kind of special Floquet systems, all right? Now we can have different flavors, different kinds of automata. So these two examples that I'm showing below, we're actually going to meet in depth later. But basically, there's a notion that there's a notion of an integrable and a non-integrable or chaotic, quote unquote, automaton that I'll explain now. And it has to do basically with the distribution of these orbit lengths, okay? So these two examples are two 1D cellular automata that are defined on L qubits, okay? So the system size is L. Now, in the non-integrable case, you see that you have these large orbits, okay? And a typical orbit in one of these non-integrable systems is going to scale exponentially with system size, okay? And the dynamics on these long orbits looks essentially random. Like if I have a very, very large system, and I look at this thing, for a finite number of time steps, I would have to wait exponentially long for the system to come back to the same state it was in initially. So basically, if your system is sufficiently large and you're restricting to times that are, much, much smaller than the length of this orbit, the evolution looks essentially random, okay? Now in these integrable automata, the typical orbit length is of order L. So it's sort of, generically, you could say polynomial in L. But, in this particular one, a typical orbit happens to scale as L. And what that kind of indicates to you is that when you initialize the system on one of these orbits, there's actually these sort of quasi-particle trails that you can see running around. So this is an example where I've sort of just, the quasi-particle in this case is sort of like this hole in this background checkerboard pattern that kind of propagates, essentially ballistically through the system. And something that's common to both of these systems is the existence of these special short orbits. I call them short because they have an orbit length L that is constant with system size, okay? So these orbits that I've highlighted here don't grow as I increase the size of the system. And these, and I'll talk about these in a second, but what you see is that basically these tend to have regular patterns of bits that evolve in a very simple way, okay? And when I say regular, I mean they have patterns of bits that are invariant under some kind of translation operation. And these short orbits are common to both chaotic and integrable automata. And what I'm going to try to make an analogy in the following slides between these short orbits in this discrete state space and these regular regions that I talked about in this TDVP way of thinking about scars. So these regular regions of continuous phase space, I'm going to try to sort of equate those with these short orbits that can exist either, they can exist both in integrable automata and in non-integrable automata, okay? So short orbits are very special in this talk. So as just an aside before moving on, I want to stress that short orbits are actually generic for translation invariant cellular automata. And you can actually prove this, it's very simple. So if you have a CA with a Floquet operator U that's invariant under R site translation, which I've called TR, basically for any computational basis state psi that is strictly invariant under translation by R sites, the Floquet operator cannot change that translation eigenvalue, okay? So that means that the only states that can be connected, if you start from an initial state that's invariant under the translation operator, that state can only be connected to other states that are also invariant under the translation operator. And there are only 2 to the R such states, okay? So if my model has a 2-site or a 3-site, et cetera, translation, there's only a finite number of states that I'm actually allowed to map to by a symmetry. So that means that for a generic cellular automaton, there's always going to be these short orbits in the sort of orbit distribution, okay? Now, these short orbits are very, very special for reasons that I'll highlight now, okay? They have really interesting ramifications for the quantum eigenstates of this classical cellular automaton. So what I mean by this is the following. The cellular automaton defines a unitary operator U, right? It's a Floquet system, and that unitary has eigenvalues and eigenvectors. These can be very complicated, okay? So these cellular automata are very interesting because even though they have a very simple action on the computational basis, the eigenstates actually don't have to be very simple. So I'll get into this now. So one thing that's nice because of this deterministic property of the evolution is that we can actually construct all of the eigenstates classically. All we have to do is take an initial state n and then evolve it under the unitary and then sum over the resulting orbit, okay? It's kind of like constructing momentum eigenstates. So basically, the quasi-energy spectrum of this unitary is very simple. You have basically these L roots of unity, where L is the orbit length of the initial state. So the quasi-energies are very simple. Like, computing level statistics of this thing would be kind of, there's no point because the spectrum is so simple. But if you have a very long orbit, this eigenstate, even though it's easy to construct, can be very complicated, okay? So in particular, for an orbit length L, it might be very plausible. It shouldn't be that hard to convince yourself that the entanglement entropy of one of these eigenstates, if the eigenstate is based on the evolution of an initial state that lives on a length L orbit, the entanglement entropy of that eigenstate is going to be upper bounded by the log of the orbit length, okay? Because my entanglement can only be as large as the number of states that are entering my eigenstate, the linear combination that forms my eigenstate. So for integrable automata, say, this example that has this typical orbit length being of length L, typical eigenstate in the system has entanglement entropy log L, okay? So that's very interesting. It's kind of unusual, right? Because we know that in quantum integrable systems, you can have volume law eigenstates, for example. But nevertheless, this is the case. You can't have volume law eigenstates in the system, basically. Whereas for chaotic automata, if your typical orbit is going like e to the L, then log of that is L. So you can have volume law eigenstates in these cellular automata. And remember, so these systems are very interesting because the eigenstates can be volume law, even though the evolution in a particular basis does not generate any entanglement. Okay, so these are kind of strange systems in that respect. And then these short orbits are very special now, kind of obviously very special, because if L is independent, if the orbit length L is independent of the system size L, then the entanglement entropy has to be constant for that state. So these short orbit eigenstates are constrained to be area law eigenstates, okay? So, I can summarize this discussion with the following, observations. Basically, these cellular automata are very interesting. There's a broad spectrum of behaviors that you can find in these systems. You can have classical and, in a sense, quantum chaos. Of course, you have to put an asterisk on quantum here because, in a dynamical sense, if you initialize the system in the computational basis, you won't generate any entanglement. So it fails that definition of chaos. But if you think of chaos as being related to eigenstate complexity, then, in a sense, these systems do support that kind of chaos. And they also can have integrability. They can have quasi-particles, much like, more conventional Floquet or even Hamiltonian systems. And finally, these short orbits are kind of special because they, you know, they're orbits that are kind of classically non-ergodic. They're very restricted. You know, the system can only explore a few states if you initialize it on a short orbit. And in the quantum picture, they yield atypical low entanglement quantum eigenstates. Okay, so my task in what follows is going to be, can we generalize this to fully quantum models? Okay, so now I don't want to restrict myself to automata. What I want to do is I want to construct fully quantum models that no longer respect this sort of automaton property of not generating any entanglement in the computational basis, but that still perhaps have these short orbits and still have this non-ergodicity. Okay, so how do we do this? This is the subject of basically the rest of the talk. The strategy here is actually very simple. So what we're going to do is we're going to start with an automaton, and then we're going to deform it. So given a cellular automaton defined by the unitary u aught, we're going to define a new Floquet operator u that's equal to u prime times u aught. Okay, and this u prime is going to have to satisfy some conditions, and the conditions that we want essentially are that this u prime needs to be locally generated. So I want to think of it as the, I want to be able to think of it as the evolution operator, for a local Hamiltonian, or I want to be able to think of it as a potential approximation. It needs to be a finite depth quantum circuit that's locally generated. And it also has to preserve some cellular automaton orbits of choice, okay? So for example, if I choose this 3-stage short orbit that I highlighted in the integrable automaton, then the connectivity graph after adding this u prime is gonna look something like this. So we'll have a whole mess over here on the left. Basically, I don't care what the system does to states that don't live on this special orbit that I chose to preserve, but for the states in that orbit, I want the system to sort of retain its, I don't want it to couple that short orbit to the rest of the states, okay? And it shouldn't be too much of a surprise that for sufficiently generic u prime, the resulting model that you get by doing this kind of deformation is, generically going to be non-integrable, and it's going to be fully quantum. And by fully quantum, I mean it does not preserve this automaton property of not generating entanglement in the computational basis. So, okay, now I just said this, but why do we think that this should work? Why do we think that this is possible? Okay, and my claim is that this is actually generically possible for any automaton. Okay, so why is that? Okay, so we can expect that this is going to work for any short orbit, this kind of deformation. So remember that the short orbits correspond to these area law eigenstates in the spectrum, okay? And because they're area law, we know that we can write them in an exact way as a finite bond dimension matrix product state, for example, okay? And such states are guaranteed to be eigenstates of some local Hamiltonian, okay? For example, there's the parent Hamiltonian construction for matrix product states. So these area law eigenstates are special because we can always construct a Hamiltonian of which this is an eigenstate. And then once you realize this, it's very simple to design this new circuit U from the automaton circuit, because you can take U prime, for example. I'm just giving an example, but you can say, okay, let me find this state's parent Hamiltonian, map it to a matrix product state, find its parent Hamiltonian, and then I'm going to perturb the circuit, so to speak, with this U prime, or I'm going to deform the circuit with this U prime. Okay, and U prime is just the evolution operator with respect to that the parent Hamiltonian of that state. Okay, so then that area law eigenstate is still going to be an area law eigenstate of the deformed model. Okay, but who knows what it's going to do to all the other states. Okay, so the resulting model, generically speaking, will feature non-ergodic dynamics and non-thermal eigenstates, essentially because we're going to preserve this special kind of subspace. And I should point out that this construction will work for any translation invariant cellular automaton because all translation invariant cellular automata have short orbits, okay? So basically, any automaton has short orbits. Short orbits correspond to area law eigenstates. Area law eigenstates can be approximated as MPSs, which we know are, you can always find a Hamiltonian of which that MPS is an eigenstate. So this is very generic. This is a generic property of automaton circuits, basically. So that's the general idea. And then for the rest of the talk, I'm going to be discussing examples. All right, specific examples that are relevant to what I've discussed already. So the first example is the PXP automaton. So I'll call this the PXP automaton. So it's basically a Floquet version. It's a specific Floquet version of this PXP model that has quantum scars or approximate quantum scars that I discussed in the beginning. So what we do basically is we take this PXP Hamiltonian and we apply it first on even sites and then on odd sites. And in order to make it an automaton, we're going to demand that we apply it always for an amount of time that's equal to pi/2 in some units, okay? And when we do this, you generate a circuit that up to some phases looks like what I've written down on the right here. So basically it's just a lattice of Toffoli gates, which are basically controlled not gates, okay? And so, you know, this is just essentially you can think of it as a Floquet generalization of the PXP model, but it's in a very special limit because you need to have this pi/2. And it turns out, it's very interesting actually, that this model is actually integrable. So this is something that I observed in the paper with Sagar, which this talk is based on, but it's also there, you know, we have people in the audience who also had a much more thorough examination of the dynamics in this automaton. And it turns out to be integrable, which is kind of surprising because the corresponding Hamiltonian model is not integrable to the best of our knowledge. And it's actually the integrable automaton that I was discussing in my discussion of generic properties of automata. This is the exact same model that I was discussing before. And the short orbit in this case, you know, all of these orbits, these other orbits have length L, but this special short orbit that has length 3, I'll call it the vacuum orbit because the initial state, or, you know, it contains this vacuum state, quote unquote vacuum state, where all spins point down, okay? So you can think of this as being kind of like a vacuum, or actually you can think of this whole sector really as being the vacuum sector with respect to the quasi-particles in the integrable system, okay? So the states in this orbit are this vacuum state and then also the 2 Néel states. And you basically just cycle between these states under the evolution. And then how do you get quasi-particles in the circuit? Well, you get quasi-particles by forming domain walls between these different vacua that live in this vacuum orbit, okay? So you get chiral quasi-particles from doing this. So this is an example of an initial state that has chiral quasi-particles in it. And you can also see that they kind of scatter and there's like sort of a time delay when they scatter. So it's some kind of interacting integrable model. You know, I'm not going to focus on the automaton, the properties of the automaton, although they're very interesting. I want to talk about how do we deform this model, okay? So I want to apply the construction that I outlined before to try to preserve this vacuum orbit, okay? So how am I going to do this? Well, let's start with the automaton unitary that I already wrote down. And then now let's consider the following Hamiltonian. So this Hamiltonian is basically just projected flip-flop operation, okay? So it just takes the pattern 1, 0 and it exchanges it with 0, 1, and it annihilates 1, 1 and 0, 0. And I'm furthermore gonna project it using the same projector that I used to build the PXP model so that I stay in this kind of Fibonacci Hilbert space that doesn't have any neighboring upspins, okay? And I added this, you don't have to add this staggered phase that I added to the model. I just added it to break some symmetries so that it was easier to do level statistics, which I'll show you in a second. But basically, you know, there's this model and you can very easily see that it annihilates all 3 states in the vacuum orbit, okay? So it clearly annihilates the vacuum state because there's no particles to hop. It also will not exchange, it won't hop any of the ones in either of the Z2 states, because if you do hop one of the ones, it's going to end up next to another one. So this projector means that it annihilates the Z2 states as well. Now, you know, then it's very clear that the composite unitary that's obtained by just e to the minus I lambda h with this Hamiltonian times U automaton has exact many-body scars. And the exact many-body scars, because this thing is just annihilating the short orbit eigenstate, is going to be the very same eigenstate that enters the automaton model, okay? But you can very clearly see that, you know, other than having that specific eigenstate, the model looks very generic, okay? So this is the level statistics. It's just the distribution of this ratio of adjacent quasi-energy gaps, which is a very common measure of you know, level statistics and ergodicity in flow case systems, also in Hamiltonian systems if you use energy instead of quasi-energy. And you see that it, you know, has a very clear random matrix form. Also, you can construct the projector onto the vacuum subspace, which is just the projector onto the subspace spanned by these three states. And you see that you know, generic eigenstates in my spectrum have 0 weight on the subspace, except for these 3 eigenstates that have quasi-energy plus or minus 2 pi over 3 and 0. And this is exactly what you would expect in the automaton. So, and you know, this these 3 states have unit weight on that subspace, as you can see here. And I guess that's what I was highlighting here. So these are literally the automaton eigenstates, but they're living in this non-ergodic, or sorry, they're living in this otherwise ergodic quantum model. Furthermore, the entanglement of this state, you can actually check that it's log 3, as you would kind of guess. So these are literally area law eigenstates, and the form of these states does not change with system size. So these are area law eigenstates in an otherwise ergodic flow case system that persist in the thermodynamic limit. And this is weird for flow case systems, right? Because flow case systems don't have ground states in their spectrum. Energy is not conserved. So this is kind of like a ground state, except it's, you know, there's no ground state, strictly speaking, in this model. So just to summarize, this is an example of the correspondence I was talking about between atypical short classical automaton orbits and atypical low entanglement eigenstates in a deformed quantum model that's based on the original automaton, the underlying automaton. And I have a few remarks that I'll make before moving on. One is that, you know, I chose this particular deformation, U prime, but there are lots of other deformations I could have chosen. For example, I could have had like arbitrary odd neighbor hoppings, or actually even neighbor hoppings would be fine too. You could add diagonal perturbations. So, you know, you can add all kinds of terms to this Hamiltonian that will preserve basically anything that preserves U1 and also the Fibonacci Hilbert space constraint is gonna annihilate these eigenstates, because the Z2 states are maximally packed and the vacuum state is empty. So there's a continuous family of Hamiltonians, or sorry, of Floquet unitaries that I'm thinking about here, really. I just showed you one instance. And furthermore, the fact that I was able to do this, as I emphasized before, has nothing to do with the fact that the original automaton is integrable. It works equally well for non-integrable automata because they also have these short orbits. So for example, you can define, this is something that we go over in our supplementary, but you know, you can define a much more complicated automaton that's also, that's non-integrable. And you can still construct new eigenstates of this, or sorry, you can deform this model still in a way that preserves, for example, this vacuum orbit. Or you can deform it in a way that preserves this isolated state. Or you can deform it in a way that preserves both. So there's like many different ways that you can deform, and you can sort of select different you can select different states or combinations of orbits to preserve with your deformations. Now, one natural question that comes to mind with this construction is what happens when you perturb the model just in a generic way. So don't perturb it in such a way that you preserve the orbit. Just take the automaton and preserve and deform it in a generic way, okay? Because that would be kind of more interesting if you could still see this, right? This effect. You can actually say something about that, and this is actually basically, we did this by generalizing to the Floquet setting, an interesting result from Lin, Chandran, and Matrunich. So basically, you can, when you perturb this automaton unitary, you can always, if your if your perturbation is weak enough, recast it in this form where the unitary is just evolution with some Hamiltonian times the automaton, okay? With this very small parameter lambda, okay? And then you can ask, let's evolve a short orbit eigenstate with you, right? So the short orbit eigenstate when we perturb the unitary is no longer an eigenstate of the model. So let's evolve it with you and then ask how long does it take to thermalize? And you can actually, find a pretty loose but very generic bound using the linear light cone for local quantum circuits. So basically, if you're interested in the dynamics of an operator with respect to this initial state, that's a short orbit eigenstate, you can basically show using the fact that basically this circuit U is still well approximated by a local unitary circuit. You can show that the thermalization time goes like 1 over square root of lambda at most, okay? At least, sorry. So this is basically, so the details and also the discussion of how you generalize this to higher dimensions is in our supplementary. But basically using only the assumption of locality of this perturbation, you can show that there's going to be a time scale, of at least this 1 over square root lambda, on which the dynamics of some local operator, for example, something that locally has eigenvalue 1 in the short orbit that you've defined, like some kind of projection operator, you can see that the value of this operator will not deviate too much from its initial value if you have a sufficiently small coupling lambda, okay? And this is a general estimate, but it's also very loose because all that it knows about is that H is local, okay? So, but it gives you some hope that maybe the slow dynamics that I've been talking about from these short orbit configurations can survive in more realistic models. So in my remaining time, I'll talk about a more realistic model that's actually based on this Rydberg experiment that I discussed at the beginning, okay? All right, so are there any questions at this point before I get into the more quote unquote realistic model? Okay. All right, so okay, now we can think about how to realize this kind of approximate, an approximate version of this non-ergodicity in, for example, the Rydberg setup. And it should be kind of more or less clear how this is going to work, given what I've already said. But this gives us an opportunity to get a little bit more into the details of the experiment. So in this experiment from Michalukin's group, we have neutral atoms in an optical tweezer array. And we can think of the system as being a spin system where the up state is a highly excited state of the atom in a given tweezer. So like in the jth tweezer, there's a Rydberg state that you can excite the atom to. And they're actually driving the atom between the ground state and the Rydberg state in this setup. And then the ground state is just the ground state of the atom. So the local 0 and 1 states are basically the occupation number of the Rydberg state, if you like. And you can define Pauli matrices that act on this subspace. And the model that they actually realize in this setup is essentially a long-range Ising model where van der Waals interactions between atoms in the Rydberg state give rise to this 1 over r to the 6th decay of the interaction. And you can also have, in principle, a time-dependent drive, time and space-dependent drive between the ground and Rydberg states that's summarized by this HI of t here. So how do we realize an approximation to the models that I was talking about earlier? So what you can do is employ a spatially modulated time periodic pumping. So basically you use a pumping field that looks like this. So basically you're turning on and off the pumping on even and odd sites in an alternating fashion as a function of time. Okay, and then you can show within some kind of time-dependent Schrieffer-Wolff-like perturbation theory, which there's details in our paper. If you're working in the limit where the strength of the drive H0 is kind of sandwiched between V1 and V2, the nearest and next nearest neighbor interaction, you can show that you reduce essentially to what we call the PXP circuit, okay, rather than the PXP automaton. So basically this parameter theta is related to the strength of the drive divided by the drive frequency. And because basically we're working in this limit of very strong nearest neighbor interaction compared to the pumping, we realize this this constraint, this blockade, Rydberg blockade constraint that I already talked about. So, and then it's very clear that when theta, this parameter, is equal to pi over 2, we get the PXP automaton. Okay, great. In fact, we actually get a family of cellular automata that depends on the interaction strength. Okay, so if V1 is much greater than H0 and H0 is much greater than V2, you get this Toffoli gate that I've already talked about, which flips only if the nearest neighbors are in the 0 state. But if you make the interaction strength stronger so that V1 is greater than V2, but then both of those are much greater than H0, for example, you can realize a gate with more controls, okay? So instead of 2 controls, I now have 4 controls. So you can make longer and longer range controlled NOT gates, essentially, by changing the interaction strength. Okay, and that's nice. I mean, it's kind of, it's also a little bit obvious if you've thought about the system, but there's something that I should emphasize or really stress here, which is that these are always going to be perturbed cellular automata. Like I was just kind of explaining this for, I was explaining the big idea here, but if you really do the calculation carefully, you're always going to be in a regime where the cellular automaton dynamics is perturbed by something that you didn't tune to preserve your orbits, okay? Even at theta equals pi over 2. So I don't even have to perturb this theta to get a perturbed automaton. The perturbation is already there because the blockade constraint is a soft constraint, okay? It's enforced by this 1 over r to the 6 interaction. So I'm gonna have terms in my evolution, for example, that include longer range interactions. And those are gonna, that's messing up, that's essentially messing up what I was trying to do. But those are diagonal corrections, so it's not that bad. It's gonna give you kind of some phase problems. But there's also subleading corrections to Schrieffer-Wolff, okay? And the point is that even before the subleading corrections kick in, you do have phase issues that will potentially help decohere your dynamics that kick in because of the longer range interactions, okay? So we shouldn't just say like, oh, this is realizing this nice circuit and then that's the end of the day. That's not how it works. There are these corrections. And you see this in the dynamics, which I'm gonna show now. So this is just, this Floquet-Ising model dynamics in the nearest neighbor blockade regime from exact diagonalization. And notice that here I've parked theta at exactly pi over 2. But I'm using this V1, the nearest neighbor interaction that is, it's large, but it's finite. And I'm also including some longer range interactions to capture the effects that I was just talking about. And I should note that this is also the V1 that is used in the experiment. So this is the exact kind of parameters that they use. And what you see, so this dynamics is for 3 different initial states in A, B, and C. And what you see on top here is you see nice signatures of the underlying PXP automaton, okay? For example, you see this short orbit, and actually the dynamics looks quite coherent, at least at short times, okay? So you see this clear signature of periodic dynamics. If I start in an initial state that has 1 chiral quasiparticle, I can see that quasiparticle propagating in this alternating vacuum background, but because of the perturbation, this quasiparticle doesn't stay coherent forever. It starts to spread, and then eventually you kind of lose a signature of it at later times. And then this is an initial state that has 2 quasiparticles in it, 1 right mover and 1 left mover. And you also see that, they scatter, they decohere as they propagate. And then this bottom panel is looking at longer time dynamics. And specifically what I'm looking at are the autocorrelator of the Pauli-Z operator in time, as well as the time evolution of the orbit weight on the vacuum sector, okay? And what you see here is that for the short orbit initial state, you have these long-lived, quite coherent oscillations that persist for kind of a surprisingly long time, given that we know that the model in this regime is not the model that I kind of was hoping to realize. And we also see that this orbit weight also picks up that a substantial fraction of the wave function is actually staying inside that orbit. And then here in the 1 quasiparticle state, we also have evidence of that orbit weight, but we also see that the sort of signature of the autocorrelator decoheres as this quasiparticle kind of runs around the system. So you can think of these initial oscillations as resulting from the fact that all of this this stuff around the quasiparticle looks like vacuum, so it's oscillating, and I'm doing a spatial average when I calculate this correlator. So as this quasiparticle propagates, it kind of disrupts that pattern. And as it spreads, the pattern disrupts even further. Yeah, so this is basically showing you that at least at early times, you can see effects that we've been talking about. But the short orbit appears to be kind of more coherent, more resilient than other states that have quasiparticles in them, okay? And I'm kind of running out of time, so I don't know, I don't want to go too long. Can I have like 5 minutes? Is that okay?
Yeah, sure.
Okay, cool. So we can take a little bit of a deeper look at this, okay, and try to understand like what do the eigenstates look like that are giving rise to this coherent dynamics, okay? What happens to the short orbit eigenstates? And to do this, what we do is we consider the PXP circuit now. So instead of the Ising model, we're just going to consider the PXP circuit directly, because we can get to larger system sizes using the constraint, et cetera, et cetera. And we're going to perturb the flow K unitary around pi over 2. Okay, so we're going to perturb it around this automaton point. And we kind of expect, based on our experience with scars, that we're going to have low entanglement eigenstates that descend from these special short orbit eigenstates. And indeed, that's what we see here. So this is a plot of the entanglement entropy in units of the page value for the Fibonacci Hilbert space. And you see that at very, very small epsilon, there's very clear entanglement outliers here. These different colors correspond to different system sizes. So these outliers are there for a range of system sizes. You can also see the sort of remnants of the entanglement pattern of the automaton, which is very strange, right? So that's what these little ETH-like domes look like. That's basically the automaton orbits that get disrupted by the perturbation. So like basically like these little sort of ETH dome-like patterns that you see are basically these orbits that have been disrupted. And you can make the perturbation even larger, and there's still a very clear, there are these outliers. There's only these special outliers that have dependence on system size, or that that are there consistently as a function of system size. And you can check that these eigenstates actually, the ones that I've highlighted, actually have predominant weight on the vacuum sector. Okay, So you can view these kind of two sets of eigenstates around plus or minus 2 pi over 3 as being kind of descendants of these automaton eigenstates. And I should also say that there's, in this model, we have a very large degeneracy at 0 quasi-energy that kind of frustrates the calculation of eigenstate properties a little bit, because you have a large exact degeneracy. So the computer isn't always going to give you the correct eigenstate. It's going to give you some superposition of a bunch of eigenstates. So that's why maybe these the 0 quasi-energy state is not so visible here. But I suspect that if the computer was giving me the correct superposition of the 0 energy eigenstates, I would see those as well. And also we can do some finite size scaling. I'm not going to go too deep into this, but what you see basically is that these entanglement outliers that I highlighted on the previous slide have an exponential in system size dependence of their vacuum orbit weight. Okay, so basically the weight on the vacuum orbit is decreasing exponentially, but the base of that exponent is very close to 1, and it appears that the base of the exponent is essentially 1 plus epsilon. Okay, so the vacuum orbit weight is roughly going like 1 plus epsilon to the minus L, which is very different from what you would expect for a random state in that Hilbert space. And also on the bottom panel, you can see that we're calculating entanglement, and you see volume law entanglement. This dashed line is log 3 here. So you see that at very, very small epsilon, you're very, very close to log 3, and then your slope grows. And the volume law slope grows with epsilon. It grows like epsilon, okay? So this suggests that there's kind of, in this perturbed model, an effective Hilbert space whose dimension is 1 plus epsilon to the L, more or less. That's kind of just a rough way of understanding the data. So long story short, when you take this model that that's kind of close to one of these automata, but it differs by some kind of it differs by some more or less generic perturbations. You can still see signatures of these short orbits, okay? And then that brings me to the summary. So what I've done in this talk is I've provided a recipe to deform any translation invariant classical cellular automaton, and I should say reversible classical cellular automaton, into a quantum Floquet model with exact many-body scars, okay? And I've also demonstrated that these exact scars persist as approximate scars in experimentally relevant models. So that's more or less the story. There's some outlook. For example, these cellular automata are kind of nice because they allow us to kind of classically model quantum systems with constraints. And there are many contexts in which such quantum systems arise, for example, in gauge theories. So can we use cellular automaton dynamics to sort of model salient aspects of gauge theories? Another thing that we could say is, can we make a more precise connection in the case of continuous phase space? And I know that Zlatko's group has some work on this recently. So there's been progress in that direction, but I think that connection is, I think, still a really interesting connection that's worth exploring further. So thanks very much for your attention, and I'm happy to take any questions that you might have.
Great, thanks, Tom. Any questions?
Thanks.
So maybe I can start. So is there anything interesting when theta is not close to pi over 2?
So yeah, there's a few limits that are kind of interesting here. So theta close to 0, for theta close to 0, it's basically, this is like the trotterization of the PXP model, okay? So like, you can imagine like, yeah, sorry, I just got a robocall on my phone and my headphones picked it up, so okay. Anyway, so when theta is close to 0, this is basically the trotterization of the PXP model. So the model has the scars that you guys found, when theta is small, okay? And then you go to theta equals pi over 2 and you reach this automaton point. At pi over 4 is kind of where it looks the most generic. And then at theta equals pi, we don't actually know very much about the model, but it appears to have some kind of like, so it's not, it's still like an sort of intrinsically Floquet model, It's not like it doesn't go back to looking like the model at theta equals 0. But we haven't looked very much into the model at theta equals pi, but theta equals pi, you know, it's interesting, and we don't exactly, we didn't study it, basically. We didn't study it too much, but it has some interesting features. So yeah, and I'm trying to remember, I think it maybe, I didn't look into it carefully enough to speak on the record about it, but that point in the phase diagram is there, and it's one that's, I think, worth looking at. Then when you get to 3 pi over 2, you're kind of back to another automaton, which is just, it's, you know, at the level of just the classical evolution, it's kind of like this model, but like with even an odd sublattices exchange or something. There's like a symmetry that kind of relates those 2 points. So basically, like the sort of poles, you know, on the unit circle, you know, that intersect the x and y axes are kind of the interesting points in the model, and then in between it kind of looks more or less generic. And the maximally sort of generic point in the phase diagram is around pi over 4. It is mostly what it looks like. And do you really think that the model is kind of generic apart from these 3 or so short orbits? So, well, okay, that's interesting, because so the PXP model is kind of weird. Like there are aspects of the PXP model that I would say, like the PXP model, I would say also doesn't look totally generic apart from the scars. Like there's sort of, in the PXP model, there's sort of 2 kinds of eigenstates. There are ones that have, you know, in your plot, you know, the plot that your group generated with the log of the overlap, right? There's sort of 2 kinds of states. There's the ones that have like 0 to machine precision overlap with the nail state. And then there's a whole bunch that have some kind of overlap. And I would say that, so I would venture to guess that, you know, at least in the static limit, you know, the PXP model does have these other eigenstates that maybe make it, I think that there's probably still some more stuff there that we don't understand. I would also say that this model, so I think, you know, basically when you're close to the automaton point, you know, I think that it looks pretty generic as you perturb, but you have to perturb it a fair amount to get rid of all of the automaton-like features. And you know, it could be that the features disappear faster if you choose a different kind of perturbation that's not just related to going along the unit circle. Like if we added some additional layer to the circuit, for example, these features might go away faster. And that's why, like this bound that we were talking about, this 1 over square root of lambda on the thermalization time, like the numerical results that we were showing, I guess over here, you know, these numerical results, like the time scale of coherence, for example, for the vacuum orbit is substantially longer than 1 over square root of lambda if you try to estimate what that is from the model that we're using. So probably this isn't the most generic way that you could imagine perturbing things. And there's some model dependence in that. But I think that the general expectation that we get from this estimate is probably correct. And then I guess, does Juan have a question?
Yeah, I have a couple. So,
okay.
So first of all, I missed the part towards the end because I lost connection. But on when you were talking of the classical PXP, what you know, we also call the 201 rule. So a couple of things there. First of all, that model, the classical one, has orbits, as you said, which are the ones you focused on, which are finite in length, and then it has orbits which are linear in the system size, and it had orbits also which are quadratic in the system size. So, and of course that model is integrable, but the things which are polynomial in system size are, but not linear, are those you think interesting in any way?
Yeah, so I mean, I suspect that because it's an integrable model, I think that this polynomial is related to kind of the recurrence time for a multi-quasi-particle initial state, more or less. So, you know, it is literally kind of, it's going to be some it's potentially a product of recurrence times, right? If you have a bunch of quasi-particles in the initial state. So I think that's probably when you have polynomials besides linear, I think that's probably what it is.
Yeah. So, yeah, Katya and Joe's mostly were on the audience and were in that, they basically wrote that paper. They might have something to add, but indeed those quadratic and system size times that are when there is an imbalance between the number of quasi-particles you have. But the other question, more general, which I don't know about this definition of scars, where this stands, is the following: is that when you add the unitary U prime, yeah, the dynamics you obtain, which is really unitary and not just permutational, keeps the vacuum, that vacuum trio isolated, right? And I think I would be more comfortable if scars emerged as a large size limit, effect, in the sense, no matter what's the system size, for finite system sizes, that's always isolated anyway. So, I would have thought that true scars should be something that emerges in the large size limit, like a transform, not something that's disconnected by the dynamics. You see my point?
So I mean, I think that is a really interesting point, but I guess what I'll say is that there are lots of examples of models that have exact scars at any finite system size, and there are many examples of these models, including so we did some work on like the spin 1 XY model. There's also some models related to like transitions between SPT phases. So these models have scars at any finite size. But what you're talking about, I think, is an interesting. I think it would be interesting. Like I would like to see examples of models where basically the idea is that scars kind of emerge in the thermodynamic limit. I think that's very interesting. I would say that it's not immediately clear to me how that would work, just because, for example, in the PXP model, where the scars are approximate, it looks like as you make the system size larger, maybe there are a sort of instabilities that set in, or there's hybridization that would tend to suppress the scars, right? So there was this entanglement data from Zlatko's group where you started to see these non-monotonicities at very, very large system sizes. And that's probably due to some kind of hybridization between sort of idealized scar states, or that was kind of the explanation that was ventured there. So there it looks like the scars, kind of like in the model that I'm talking about in this talk, where we don't sort of fine tune the deformation, it looks like they kind of go away in the thermodynamic limit. And that's kind of generically, that's what you would expect if you took a model that has scar states at any finite size and then perturbed it, and then used like Fermi-Golden rule type reasoning to look at how the exact scar states hybridize with the perturbation. So I think what you're talking about is very interesting, but I don't know how it fits into the models that have been studied so far.
Well, there are some models which are like that, and we can discuss it separately. But
okay, yeah, I'm just not aware of them, I guess.
Okay.
Any other questions? Okay, if not, because we ran a bit over time, maybe we can officially stop here, and yeah, we can continue chatting if anybody has more private questions. Okay, thanks.
Yeah, that sounds good. Yeah, thank you.